and then I'm also going to walk you through a demonstration of accessing large amounts of ICESat-2 data in cloud and some processing.
Hopefully everyone's able to catch that on Zoom. And Lisa.
Yeah, hi everybody. I work at NSIDC and most of you was happy to facilitate you guys to work together. I will be watching soon for questions.
All right. So for this presentation, we can all access, actually, would you mind sending the slideshow link here to everybody on their email so people can open it up? You can also access this presentation here with this QR code. We'll have the slides to you in just a moment on your email, so you can follow along there. Click on the URLs and things like that. Before we dive into anything else, we want to go through a code of conduct, which we adhere to in CryoCloud. So I'm going to just run through this really quickly so we all are on the same page with how we're going to run this workshop and also work on CryoCloud together. We strive to create a welcoming and inclusive culture that empowers people to provide outstanding open science, and that requires an open exchange of ideas balanced by thoughtful guidelines. It would be impossible to list everything we can do to create a more welcoming space, and we know each of you will include your colleagues and think of things that we haven't thought of, but when in doubt, go ahead and look at these principles if you want to know about how to interact with each other. So our principles for guidance are practice empathy and humility, participate in an authentic and active way, exercise consideration and respect in your speech and actions, assume that everyone we work with is doing their best, listen carefully and actively, ask questions and seek to understand each other's context, encourage people to listen as much as they speak, attempt collaboration before conflict, treat other people's identities and cultures with respect, be mindful of your surroundings and of your fellow participants, alert community leaders if you notice any dangerous situations, someone in distress, or violations of the code of conduct, even if they're inconsequential. Please be respectful of differing opinions, viewpoints, and experiences. Give and gracefully accept constructive feedback. Accept responsibility and apologize to those affected by our mistakes and learn from our experiences, and focus on what is best, not just for us as individuals, but the overall community. Does anyone have any questions about that? Great. And if there's any violations, you can send an email to us through each of us individually, Wilson, myself, Andy, or Lisa. You can also email anybody in the CryoCloud team. So as we get started, I'll first give you the incentives for why we want to work in the cloud. CryoCloud will help you accelerate your science, as a lot of people have discussed in this meeting, and it makes open science easier. In the cloud, you can do data read-ins 1 to 2 orders of magnitude faster than you would otherwise. It makes collaboration easier. It helps to eliminate technology bottlenecks. So we have an environment that you can hop in on. You don't have to build your own, it's already working. Data access, we have a lot of code for that. So you can access some of the cloud data sets really easily. And especially for our early career scientists, people just starting out, those are some of the things that they are all replicating and needing to spend weeks on. They're especially going to benefit from this. Also, CryoCloud is easy to use and customizable. It should be similar software to what you have on your local computer, on an HPC, and in this cloud. So it should look very similar. How many people already are working on Jupyter notebooks or Jupyter Lab, just so I can get a read? Well, most people. Is anyone primarily using MATLAB or R? Okay, cool. We do have MATLAB and R kernels. I'll show you where those are. Most of what we're going to be talking about is in Python, but you get to see a lot of what the benefits are working in Python. But all of this can also, a lot of this can be done in MATLAB and R as well. So from this workshop, from the CryoCloud standpoint, you'll understand opportunities and challenges working in the cloud environment, learn about the tools needed for working in the cloud, and you'll gain access to CryoCloud in this first hour and explore its utility in your research problems. We'll talk first about open science with NASA, introduce the cloud, get to know CryoCloud, and do a demo. You'll do an important info and wrap up. We'll give you all the links that you need to work on CryoCloud and troubleshooting. Then we'll get into some tasks and do some tutorials. So what we need to do first is make sure all of you are able to work in the cloud. So if you can go ahead and jump on hub.cryointhecloud.com, make sure that you have access and everything is working there. If you don't have access and you haven't filled out the Getting Started survey, that form is found here in this first line with this QR code. Everybody else, if you're already on the hub, I'd like you to work on this onboarding survey. That gives us a lot of information about your background in the cloud and gives us the information we need to meet some of our objectives for CryoCloud, our deliverables for NASA.
I should have sent you an email with the slides. Did you get that?
I probably should have done it. That's what you said.
Oh, probably doesn't have, doesn't include everybody. Let me. There's too many emails. Oh yeah, that'll be best, probably. Okay. Is everyone good online? Just let us know if you have any questions.
Oh, I see. Did anyone else?
What's that?
The slides. The
Slides.
I'll walk us through that in a second, but it'll be the 16. Yeah. We're gonna be doing some big data stuff. And yeah, I'll walk you guys through that really quickly. I'll do it right now so you can see. We can all just log in. It's better to get it going right now before anything else. So if you get to CryoCloud, you log in with your GitHub username and ID and password, and go to node. When you choose your node, you can go to 16 gigabytes, and we're going to be in Python. You don't see the medium computer there. If you're already logged in, I can help you change servers. You can just let us know. It'll take a little bit to warm up because we have a lot of people that'll be opening up servers. So we may as well do that in the background right now.
I started off with one.
Okay. For those
Seattle people, man.
who started out the wrong one, go ahead and go to File and go down to Hub Control Center. Hub Control Center, yeah. And then press Stop Server when that opens. It's a big red button. Stop Server, and then you log out on the top right. And then you'll be able to close out your windows and then open it back up.
Okay, you need to plug in. Okay, yeah. Yeah.
Is everyone able to get to the onboarding survey? Okay. Okay. Are you on a NASA computer? Okay. NASA computers, we're having problems with our Google Forms, FYI. How many people are still working on the survey? Okay.
Was there something that you needed to work on to like fill the onboarding out before you could start a survey? There's no connection there, right?
With the survey, can you check and make sure that he's has it? Wait, does he have access to the hub? But has he been able to open the hub?
Not yet, no.
Okay, so he needs to. We need to invite him to get to have it, and he needs to.
No, that I should be made last night, but it's.
Yeah.
Yeah.
Oh.
Different than that. Okay. Okay. The software is very
Yeah.
Okay.
Do you want to go that?
And it's minor,
It's fine, yeah. All right, so we'll give this 2 more minutes and then we'll get started with the rest of the workshop.
Just for this onboarding survey, I think I put one up a while ago. Is this the new one for this?
No, you can just leave that. I should put that in or email.
Yeah.
If you've already done the onboarding survey, you don't need to do it again. Wilson, how are we doing? Okay. Give it another minute. And we can just move on without doing the onboarding survey for him, and he can fill it out another time. All right. Good to go. All right, let's get started. I'll give you guys a second to come back to this. All right, so now we're going to start give you a little bit of background on CryoCloud and what NASA is doing with their kind of open science push. NASA has recently declared that science done in a fundamentally more open way is the way of the future. Open science, if you aren't aware, is defined as the principle and practice of making research products and processes available to all, while respecting diverse cultures, maintaining security and privacy, and fostering collaborations, reproducibility, and equity. So CryoCloud was kind of born in NASA's open science revolution. They created the Open Source Science Initiative, which is meant to make science more transparent, reproducible, inclusive, and accessible. And the Transformed Open Science program is under that umbrella, and it's meant to help break down barriers of access for historically excluded communities and increase opportunities for collaboration while promoting these goals for the Open Source Science Initiative. And all of this is kind of culminating in this year of open science that was declared first by NASA and then now by the US federal government and 80 academic institutions. So it's a huge thrust towards open science by everybody in the United States. And next year, hopefully, will be the International Year of Open Science. So that's what we're working towards. And one of the ways that we can conduct open science is through the cloud, doing more collaborative and reproducible science that way. For background for you guys, the cloud is 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 the cloud, 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 is the cloud. All right, can everyone hear me on Zoom okay?
No.
Okay. Great. All right, I'll continue. Suzanne, okay.
Ooh. That was terrible.
I think I need to just. The owl is not my favorite.
It's a cloud. It's
Okay.
a cloud. It's a cloud. It's a cloud.
All right. So moving on, make sure everyone online is muted. So as we have this cloud that we can now have access to, we will need to have concepts and skills to better use the computer as a tool of thought. And this is kind of going to demonstrate how we can use the cloud. So practical skills we need to do open science will be version control, programming, process automation, data analysis, software testing, documentation and publishing, continuous integration, and reproducible containers. And these are kind of the tools on the right-hand side that we can use for that. And demonstrating how those were used in the cloud was done in the Stats 159 course that Fernando Perez taught at UC Berkeley. It's a course that over a semester, these students put together a scientific project that included a Jupyter book-based site that they built that includes a main paper, supporting analysis notebooks, code and tests, and reproducibility. So someone could click on this notebook, run all the code, and interact and play with it, change the code within Binder, which is a tool for reproducibility, and have their entire scientific process right there to make it super transparent and reproducible. And so this was taught over the course of one semester in an undergraduate course. And what's cool about it is that these courses have 50 to 2,000 students working in it, and they're working in the cloud for $1 to $2 per semester per student. And so this is actually a very cost-effective way to teach this amazing skill to students. And we're also making science more reproducible and transparent in that. So the cloud can be very cost-effective if it's on a system that is worked out to make it cost-effective, because you can also easily spend a ton of money if things are not set up well. So with that, new spaces and organizational models are needed to work in the cloud. And this is where we get to CryoCloud. So CryoCloud kind of came out of the ICESat-2 Science Team meeting that happened last May. There was a cloud computing and open science panel where people talked about the fact that the cloud had non-intuitive pricing structures, documentation was poor, computing options were poor, and infrastructure was non-intuitive. It was costly to use. Some people were racking up thousands of dollars without meaning to. they were worried about the time to transition to workflows, their workflows to the cloud, intellectual theft, and not sure that the cloud was actually more collaborative or faster. And Joanna Milstein, who is a graduate, or she just graduated, she just defended from MIT, and myself were surprised by this response because we didn't have this experience working in the cloud. And we decided to build CryoCloud to deal with that. And the reason why we didn't have these issues on the cloud is because we worked on a cloud that was created and supported by 2I2C, the International Interactive Computing Collaboration. It's a nonprofit that came out of a collaboration between the University of British Columbia, Pangeo, and Berkeley, who all set up hubs, created these Jupyter hubs in the cloud that were catastrophically successful. And a lot of people wanted them, but they weren't able to actually provide that service through their institution. So they created this nonprofit, 2I2C, to be a service provider for the interactive computing infrastructure for Jupyter hubs. And their kind of mentality is to contribute back to the open source science community. So everything that they build is also going out to the community at large and is easily transferable to other systems, other vendors. So we decided to partner with 2I2C to build a cloud computing platform with bumpers. And so the goal for CryoCloud is to provide a simple and cost-effective managed cloud environment for training and transitioning new users to the cloud, and also determining community best practices. So as we're going, we're trying to figure out how we all work best together, what tools need to still be built, how different groups, small teams, large teams work together, how individuals, who needs it, who doesn't need it. That's what we're trying to learn through a lot of the surveys and interactions that we're having with you. The CryoCloud's built for you guys by cloud experts to help process data faster and democratize science. CryoCloud's meant to be persistent for at least 3 years. Hopefully it'll be a lot longer. It's been pretty successful so far, so we think it will be. You have access to servers that have 32 gigabytes of RAM and 4 CPUs for all the users. And there's an option to have larger servers if you bring your own cloud credits, if you want to do larger, massive computes. We're creating new tools, so a personal cost monitoring tool to understand your usage, and improved intra and intra-hub collaboration. And then 2I2C is also scaling because it's a new nonprofit. And so we're providing the community surveys and feedback for them to improve and make their services better and more cost effective. And so what ends up being built is this community hub. It has cloud infrastructure, it has support and services associated with it, custom environments and online content. And all you need to do is to authenticate with your GitHub username and password. That's all we need. It takes 30 seconds for us to get you into the organization up. So it's super simple. And what we end up trying to produce is this unified experience across all of your different, the different places that you might be computing. So to look the same, no matter whether you're on your personal computer, on an HPC or in the cloud. The Jupyter lab setup will have a full terminal window. It has file management. It has markdown, ability to look at and edit Markdown and preview it. There's launcher to access different tools, different ways of viewing and editing your data. You can also do normal computing. So we have a virtual desktop where you can access things like QGIS, and QGreenland is loaded onto our QGIS. We also have file synchronization that works very similarly to Dropbox that you can use. Wilson is the expert in using that to set that up. There's documentation on there to use it. I'll point out where all of these are. CryoCloud has a versatile choice of computer language and server size. So you will see a drop-down menu for R, MATLAB, and Python. And so you will be able to use something like RStudio or MATLAB from this system as well. The node share, the way this works is you have anything from 1 gigabyte to 32 gigabytes that you can select. And basically the server is up to 32 gigabytes and 4 CPU. If you are running like a notebook or a bunch of code that requires only 8 GB, we suggest that you use only an 8 GB server, and then you end up sharing your node with other people, and that makes it more cost effective. But definitely if you need more than that, then use it, because your server will shut down if you go much over what you choose. So that's just the thing to keep in mind, is to watch your memory, and I'll show you how to do that, so that you make the right choice for what your needs are. Let me get rid of this. That's it. Yeah. So what's really cool about CryoCloud is that it brings together different kinds of users all into one space. We have developers and users and a lot of different types of people working in CryoCloud, and that helps to accelerate feedback and collaboration. So over here on the left, you see a notebook. This integrates data from ICESat-2, MODIS, and Landsat all into one place, and we're using tools like X-Array, IcePix, and Earth Access. And a lot of these are being developed, and they need to be developed for you as users, and you may find bugs. And if you provide feedback, and a lot of these developers are actually working in CryoCloud or similar environments, you can provide feedback. It gets to be very instantaneous for the developers to actually go fix those bugs or create those tools that you need. And that really, because they're working in the same environment as you are, it makes it easy to test. And so we can really accelerate this building of tools that you guys need, and make it easy to actively participate in creating tools that are designed for you. So now what we're going to do is do a CryoCloud demo. So let's do a test drive. So if you didn't already set it up, go ahead and open your at hub.cryointhecloud.com and select Python and select the 16 GB server, and that will take a moment to open. How many people are already have already opened it up? Okay, well, great. We'll give people a few more moments. So what you'll notice when you open this up is if it's not already open, you can click this folder sign right here, and this opens up your files. I have a lot more than you do. Whatever files you put onto CryoCloud are yours. No one else sees them. The only folders that you will see that are similar to others are the shared public, and potentially shared read write, and the desktop. And shared public is a folder where you can share openly with other people. You have read and write access to that. So if you delete something, it deletes it for everybody. So please be careful about deleting other people's things in this shared public folder, but that is a way that you can share things very easily. The shared read write you won't have access to. Shared is a folder where admins have placed data that a lot of the community may need to use. So Q Greenland is located in here. I have a coastline polygon for Antarctica in here. And we'll have the CryoCloud demo, which I'll show you in just a moment. And everything else is yours. So if y'all wouldn't mind, we can open up the shared, go to the CryoCloud demo, and open up the CryoCloud demo notebook. You can come back to this at any point. It gives you access to the PowerPoint, how to open the cloud, something we'll do in just a moment, which is clone the ICESat-2 Hack Week Jupiter book, and so on. So first I'll give you a demo of everything that you can do here. So we have this file system over here on the left. You can navigate through it like anything you would normally in your own computer. The plus sign is the launcher. This gives you access to all of the tools. You can open up a new notebook. You can access the desktop, which is right here.
Wait, what plus sign? That plus sign? Oh.
Oh yeah, the plus sign is right up here in the top left.
I'm assuming it says there being a message saying their dashboard is not connected.
I have not run into your dashboard is not connected. What were they clicking on? Oh, they weren't actually able to open the hub? Is that what happened? Okay, because that may just be a login thing. So here, this is the desktop, all of your files, your file system, which is located on over here on your file system, that is also accessible here in the desktop. So when you start creating images in the cloud, you can actually visualize them in QGIS. We can also add other things if you need them here, but this is nice to just be able to access Q Greenland and QGIS and navigate around. Your folder system is down here. There's an internet browser as well. Sync thing, again, you can open that up and get it to, you basically create sync thing on your computer and on the cloud, and then the files that you drop in there are instantly available to both. And so it makes sharing with your computer a lot easier. Console, this is a basically a Scratch console, so you can run code, look at variables and things in that. Anything you open, you can move to different locations to view it differently, put them side by side, that sort of thing. And there's terminal, so this is your command line. You can do everything that you need to from this command line. You can also do it from your notebooks easily. Text file, markdown file, just a .py file. All of that's located and accessible here. Then going across the top here again, you can create your own folder in this file system here. You can upload data using this. You can also just drag and drop. So I can actually, I'll share my full screen here so you guys can all see this. Where is it? Does anyone see it? I guess it's this one. Yeah. So if I want to share a file, I can just go in, take this, drag and drop it, and it'll take a moment to add it. And that's how you can drag and drop things into the cloud. It does take a minute. So if you have something big, know that it will take a moment. This is refresh, and then git clone. You can, this is one of the many ways that you can clone program or through the GUI to get a GitHub repository onto CryoCloud. Another thing that is really useful that you can do is you can favorite things. And so it gets added to up here and makes it easy to find a folder or a file system if you want to favorite something. Also to take note of is we just opened up the CryoCloud demo. You'll see that there's a green dot here. That means that there's a kernel running for that notebook. And even when I close that notebook, that kernel will continue running. And you can actually like just shut that down here, this kernel. You don't have to, but as you shut that down, it saves you more memory. Now moving down on the left-hand side, this second button here shows you all your open tabs, shows all your kernels. So I have a console still running and the kernel, and I can shut these down from here. And then there's the terminal open. There's a Dask dashboard if you run Dask for parallelizing your computing. And that helps you to monitor what each of the CPUs are doing. This is also, this button here allows you to interface with GitHub more easily. This right here is and basically accesses the content from the notebook that you're looking at and outlines it. So you will see demo CryoCloud here, follow along. That's the next heading there. You can move throughout the notebook really easily by selecting this. So if you're like me and you create notebooks that are gigantic, this is a way to move through those really easily. And then there's extensions that we don't really need to talk about. Over here, this button on the right-hand side gives you access to metadata for your notebook that you have open. Usually don't mess with that, but maybe if you're building tools, if you're creating tests for your notebook, you might use that. This second button here, yeah. Oh, from the cloud onto your actual computer, I'm guessing. The cloud does not communicate with your computer directly, so the answer, as far as I know, would be no for that, unless you SSH into it. Does that answer the question? Cool. Yeah, all right, so continuing down with this button here, am I moving at a pace that's okay with everybody still? Okay, everyone online, good to go. Definitely chime in. I will change anything if you need it online. We want to make sure we're working well with you guys too. All right, so this button on the right-hand side is kernel usage. You can look at the number of CPUs that are being used in your memory and things like that, percentage used. One thing to also take note of is this mem number down at the bottom here. That's the number you want to look at as you're running notebooks to see what size server you might need. So you'll watch this number go up as you start running things and reading in data and things like that. So if that number gets above whatever computer size you have, it'll go a little ways and then it'll shut down your server and you'll have to restart. So just keep that in mind in choosing the server size that you use. And then there's a bug tool over here on the right that isn't quite hooked up for debugging. Moving through the top here, there's help where you can get a bunch of resources. In settings, you can change like the way that your system looks. So font size, all of that gets moved up there. This is looking at all of your active and tabs. You can move through them here as well. Another way to access your GitHub code kernel. This is something that interfaces with the notebooks you're running. So plus, obviously, in your notebook adds a cell to your notebook for coding. This cuts the cells, copies selected cells, pastes, plays, stops, interrupts the kernel, and restart the kernel, so that gets rid of all the variables and things that you've run. Yeah, you can download your notebook. Also, something that's really important for this is a code cell here. There's a lot of different, not only do we have buttons to do things, but we can use shortcuts to be able to move throughout the cells and change cells. So right now this is a code cell. I can press escape, which exits me out of actually like typing within that cell. I can press M, and you can see this up here changed from code to markdown. And then you can press enter to start working on that cell again. And so when I type something like a heading and run it, it comes out like that. So there's a lot of different shortcuts that you can look up for using your notebooks. Another cool thing about working in these notebooks are magic cells. So magic cells or magic commands looks something like, this is one of my favorites, matplotlib widget. This allows you to do interactive plotting with all the plots that you create and makes them a lot nicer. So you can read that in at the top of your notebook, and all of your code down below that will run that well. You can do things like time it, You can automatically have the notebook sense if any changes have occurred to any of your libraries, and it'll automatically read those in. There's a lot of different magics that you can do, so that's really nice. Another thing you can do from these notebooks is you can access terminal and run code in terminal interactively in your notebook. So I can check my current working directory. That tells me what that is. I can do anything in terminal using this exclamation point within the cell. And you don't actually have to open up terminal. You can read things into your notebook, in and out of your notebook in a terminal, which is really nice. So moving on, so the kernel, interrupt kernel is just like stopping your kernel if you're running something in the middle of it. Restart kernel will get rid of everything that you've run and start over, and shutdown kernel will just stop it. You can run all of your cells in the same way here, different views that you can have. You can edit. A lot of the things that I just showed you have buttons here in edit. And the thing that is probably one of the most important things for you all to know is this hub control panel. So if you go to hub control panel, it opens up another window. This is where you will see the stop my server button. So anytime you need to change the size of your server, or if you're done with your session, press the stop my server button before you log out, and that'll stop it. So CryoCloud basically has this thing built in where if you forget about your server, it'll continue running for 90 minutes until, if there's no use for 90 minutes, it'll shut down. And that saves us a ton of money. So you don't actually ring up a ton of money accidentally leaving your server open. So if you forget and you leave it open, that's great. I mean, it'll shut down. But if you if you're signing out, the best way to sign out is to stop your server first. That stops the cost charging, and then to log out here on the right-hand side. You can also switch servers here and add new servers if you want to there. So that's the main way to help us with CryoCloud saving money. Are there any questions right now with the demo? Oops.
How did you get to the stop the server again? Was it edit? What was that file?
So you go to file and then
Okay.
hub control panel down at the bottom.
Got it. Okay, thanks.
And you can save your current workspace as and things like that. Basically, when you exit, as you saw, when you exit out of CryoCloud, it saves whatever notebooks are open, unless you didn't shut it, unless you still have something running and you open up another one, then it will come up with the clear workspace. And I would just shut down that server. If you really want the old files open that you had open, just shut that down, open it back up, and they should be there. But these are all the files that I left on here when I was last on here, and that it opens me back up right where I was. So that's a really nice part of this. Are there any other questions from the demo so far? I'll get to some of the troubleshooting and things in just a moment.
Question to the automatic shutdown. So if I just the notebook running and there's just the process, whatever, looping over a lot of files that runs for a long time, longer than 90 minutes, but I don't, I walk away from the computer and don't use the mouse or anything, will it then shut down?
Yes. So there is a line of code to prevent that from happening. That code, we just have to make sure, you have to make sure it doesn't keep the server running indefinitely. But there is a line of code that we can run. Like if you reach out to me, I can give that to you. It is in our Slack channel. But yeah, there's a line of code to keep it running for as long as the amount of time that you need it to keep running. Another thing to keep in mind are pip installs. And just so you can I can demonstrate that for you. This is another magic command. So our environment should have most of what you need. If it doesn't have something that you need, you want this to be reproducible, you can add this at the top of your notebook, pip install by GMT. So this will do the pip install into that specific kernel. The percent at the front makes it do that. So you want to make sure that all of your pip installs are in your notebooks and they say this to make your kernel work properly. And that'll make it reproducible. So when you share that notebook, someone else who's also on CryoCloud will have to install the same things as you. So it makes it really nice. Another thing that you can do, if you have something that takes a long time, or you won't have multiple packages you want to install and make that easy for you to do again. We have how-tos and how to, in background work under Python installation and environment, and there's information about how to create your own environment and create a kernel from that will stay on CryoCloud, and you can use that environment over and over again if your environment is significantly different. So that was written up by Scott Henderson recently, and so you can do that here. That's in our Jupyter book at book.cryointhecloud.com.
I have a question about pip install.
Yeah.
What if I just do exclamation mark pip install?
So usually that will work well, but it doesn't necessarily, if it's certain installations may not put that in the right kernel and may not make it accessible to that kernel that you're working on in your notebook. So best practices is to use % pip install rather than the exclamation point. You can do it. It just doesn't necessarily install into the right place every single time. All right, so finishing up with the demo side of things, housekeeping. When you're using the hub, we ask that you keep your data storage below 10 gigabytes unless you talk to us about it. So it costs about $90 per month to store 2 terabytes of data. So it costs money to store this data. So as you don't need data on the cloud, or you've downloaded it, gotten it off the cloud, it's best to delete that. There's also a lot of scratch notebooks and places where you can keep temporary files. And ideally, we're working out a document to talk about how to do this, but using these scratch buckets and temporary storage, you can get rid of most of the intermediate stages that you would normally have in your workflows and only have the end products. Because you can stream data really quickly and reproduce those really quickly, you don't really need to store the intermediate steps. So it really reduces the amount of data you actually need to store. So we're working towards that, providing you with documentation of how to do that. If you end up wanting to store more than 10 gigabytes of data, just in general, we have to potentially apply for more cloud credits for that storage. And we're discussing, we have a community S3 bucket. So if you need access to faster data read-ins and things like that from an S3 bucket on the cloud, you can talk to us about that. There's been a lot of talk about it in our Slack channel from Dennis Felixson, because he started one. Pip installs, again, best practices that I just talked about are here. And then just what I said about the hub automatically shutting off after 90 minutes. And if you can remember to go to the hub control panel and stop server instead of letting it just run out. For troubleshooting, because we have this entire community of expertise, it kind of makes answering all of the questions you may have a lot easier. People are much more available to and experienced in doing that. We have a range of expertise on CryoCloud. So so a lot of people you see in this room might be responding to the questions that you have. We have our Slack hub users question. You can ask questions, any questions there, talk about issues, and we can point you in the right direction for where you might want to ask that question. You can report specific issues on that need to be added or fixed on the hub at our GitHub issues page. For our specific CryoCloud hub. For general hub questions and troubleshooting, you can ask the larger Jupyter Hub community at the Pangeo discourse. And you can also email us, the CryoCloud team, to help advise you with anything or get you more resources that you might need. If you use CryoCloud, please cite us in the publications that you create. That's right here. I've already cited this on one of my papers. That'll help us get credit and know how big our impact is. And we also have a CryoCloud Zenodo community where people can place slides, code. You can put your publications that are done by CryoCloud, things like that. That can be linked into our Zenodo. Here's the cheat sheet for all of our resources, our website, Hub, Jupyter Book, GitHub, the Slack, and everything there. If you want more skills, there's online tutorials. The ICESat-2 Hack Week has a ton of resources, how to use GitHub better, ICESat-2 data and processing, NASA data access. There's a lot of information on our Jupyter Book and the NASA OpenScapes cookbook. There will be a CryoCloud advanced tutorials I mentioned before at AGU on the Sunday right before that'll run for the entire day. And also definitely participate in one of the hack weeks that we have. We just did the ICESat-2 Hack Week on CryoCloud. The GeoSmart Hack Week will happen on CryoCloud in a few weeks, and that one's on machine learning. So let's do a quick task in CryoCloud to get started before we jump into the rest of the tutorials. So for this, we're going to clone the ICESat-2 Hack Week. Or sorry, that's not what I meant to say there. CryoCloud, Jupyter Book, into your hub. And to do that, in the demo that I showed you, all of the code for doing that is here. What you'll need to do is if you go into this file folder area, if you click on this folder, you can place the CryoCloud website wherever you want. This is going to be our Jupyter Book with all of the tutorials. So you'll need to have these so you can access the tutorials. So I already have it here. Basically, what you'll need to do is you'll press the plus sign, go to the terminal button here, and you can CD to whatever notebook or directory that you want to be in. I have it on my top folder there, so you don't have to move it at all. So you don't necessarily have to change directory to any directory. And then you can either copy and paste from this get clone here. You can push the button.
Do you want it to be the CryoCloud rather than Happy?
Shit. Yes. Let's do this the way that we normally would do this. Let's go to our github.com/cryo in the cloud. Cryo in the cloud. You'll go to the repositories and go to the CryoCloud website. So the repositories tab here, CryoCloud website. And then this green button here, if you click on that, it opens up, will clone via HTTPS. And so it gives you basically the link right there. You can just click these two boxes, that'll copy that. And so in our terminal, we can do git clone and drop that link there. This can obviously be done using this, this git interactive button here in lots of different ways, but git clone and dropping this into terminal will work. I already have it here, so it tells me not to do it again. Let me check. No, let me change that really quickly. It's now in the PowerPoint. Yeah, so you can clone it from there too. Is that change there for you? Thank you for catching that. Yeah. Instantaneous. So yeah, so how'd everyone do? Has everyone been able to clone it? Do I need to walk through that again? Raise your hand if you're still working on it. Okay. Few people? Yes.
Like 8 days ago,
Uh-huh.
but there have been updates.
There have been updates.
What? The latest, changes. Are you still-
No, so what you'll do is you'll change directory into CryoCloud website. So that'll take you into the actual repo. And then you'll say git pull. And git pull will pull all the new changes. I'm stashing because I made changes to it. So yeah, you can see I updated. That's how you will update the Jupyter book if you ever need to in the future. That's all on GitHub of how to update that. Yeah. No. And everything that you pip install will only last for the current day that you're using it. So as soon as you get off and stop your server, it will be erased. That's how you, if you want to add something to your environment, that's how you go in and create this new environment and create a kernel for it. And then that will be persistent, and you can have that over multiple uses. If you need certain things installed, that would be a situation where you create a GitHub issue, or you reach out to me or the CryoCloud team, and we can talk about how to install that. Or if we would use that as a community, or how that would work. So the question was, what if you want to make a like system change or change to the environment or something like that? And so the answer was that those changes are not persistent unless we change it in our GitHub image. So that would be something that an admin would be able to change, or you can create persistent environment changes and things like that through the documentation I showed you on our GitHub, our Jupyter book, if it's just the environment. Uh-huh.
When I'm on my command line, it shows like using an environment called notebook. But when I'm looking at the tab in my GitHub for all the notebooks, it's that I'm using Python 3 iPython. Is that the same as notebook?
I believe not. That's slightly different.
But I don't seem to have. But when you go to the Jupyter tab, and it doesn't seem to have something called notebook listed at the top. Yeah, that seems like
we've actually had this conversation before, and I'm forgetting what happened. Well, actually, so I think they might be the same. I think the kernel, where are you seeing the notebook? Oh, right. That's accurate. That's accurate. You have to install it on your notebook. Just the %pip install. Yeah, you can use exclamation pip install, but like we talked about before, that might not necessarily make it to your kernel. It usually does, but it might not. So so yeah, anything that you pip install to your terminal may not make it to your actual notebook terminal. So just do the %pip install on your notebook, and it will be perfect. It'll add to that. The way that you like make persistent changes to an environment is by creating a new environment, linking that to a kernel, which would give you essentially a new button on this launcher to be able to access that kernel. And you would also be able to access that kernel through this drop down here. Yeah.
Didn't we have R, maybe you should do Python there on the top?
So the R is separate. It comes in a Jupyter Hub. You access it from a Jupyter Hub, but when you open it into the R image, like at the very beginning when you're choosing your servers, one of the buttons that comes up will be R Studio. Yeah. And if you're using R or MATLAB and you need us to change the image, because I haven't played with those. If you need something changed in like the environment or whatever, we can work on that. But I haven't worked with anybody to change those yet.
On the environments, I did first thing on the info inside the notebook and said that the environment was notebook. I think they are the same.
They might be the same. You weren't necessarily running that in. Yeah, I think that one's named the same, or that one will be the same. They'll be linked, but your notebook may not necessarily be running that environment if you have other kernels or, yeah. It's a little confusing. Thank you, Tyler. Any other questions so far? Cool. Andy, do you want to get started?
Sure.
Okay. So next, actually, let's take a quick break for everybody. Let's come back in, should we say 5 minutes or 10 minutes? What would people prefer?
I think there's somebody online that we're trying to talk about.
Okay.
Yeah.
Let's come back.
In the wrong directory, but I'm helping that.
Okay, let's come back at 2:05. So as we're coming back, the one thing that I did want to note really quickly is that the way that we talked about doing installs was %pip install. There is also %conda install if you have dependencies that need to be added as well, and it'll solve the environment for that. It's pretty slow. The cool thing is that there's a new IPython update that we haven't added yet to our environment, but will very soon. And when you see that come across our Slack, apparently that has a %mamba install. Mamba does the same thing as conda, but much faster. So you'll be able to do these installs if you have a lot of dependencies in your notebook much more quickly. So look out for that. But you can also, just so you know, you can use %conda or %pip install or eventually %mamba install. So now we're going to get started with Andy's first demo, showing you Earth Access and how to use that to access NASA data. So Andy, go ahead.
Okay, great. Thanks very much. Can everybody hear me online? Someone give me a thumbs up or a message. Anybody?
Might be.
Okay. Excellent. Great. Thank you very much for responding that. Okay. So, yeah, my name's Andy Barrett. I'm from NSIDC. And this is actually a tutorial that I developed or built on and presented at the ICESat-2 Hack Week in Seattle 2 or 3 weeks ago. And I think it's a useful one to present here because Earth Access is a tool that allows you it deals with a lot of the problems that we have with authentication. And those of you who've used NASA data know that you need to have an Earth data login, username and password. When we're working in the cloud, we also need to be able to or have to get tokens and credentials in order to be able to do that cloud work. So we realized quite early on when we were doing this, or Luis Lopez realized quite early on when we were doing this, that we needed to simplify that. You didn't need to know about all low-level libraries and write lines and lines of code in order to go through authentication. So Luis developed Earth Access. It not only deals with authentication, it allows you to search the whole of NASA's data sets using CMR, which is the Common Metadata Repository, and it allows you to access that data, and it is, I guess, environment agnostic in that you can use pretty much the same commands to search for and access data if you're on your local machine as if you were in the cloud. There's a few little extra nuanced steps and stuff, but essentially the interface is the same, and that's great, especially if you want to develop your notebook in the cloud and then you give it to someone or someone takes it and they want to work with it locally. You can do pretty much the same thing, and that's kind of where we should be going. Things should be easy, and dealing with all these little nuances gets in the way of actually doing science. So that's why Luis developed Earth Access. Now I'm going to first show you how to get to the tutorial notebook, and I'm actually going to open up an empty notebook and run through the commands that way. Feel free just to follow along in the tutorial notebook, or if you want, just open up a new Python notebook and just follow along as I type in. Hopefully I'll go slow enough that will allow you to do that. So first steps, let's find the tutorial notebook. That's in, you've just cloned the CryoCloud website repo. So let's go to CryoCloud website and open that up, and then go to the book directory and open that. And then the tutorials that I'm going to be presenting are in the external file. So click on external, and then the tutorial notebook is ICESat-2 Earth Access.ipynb. And just double click and you should see something like that on your in your terminal. So this is, I've kind of laid out and tried to describe so that you can do this at home and get help that way. Yeah, let's just close this. Thank you. Right. But what I'm going to do is to create or just open up a separate notebook and just run through the commands on their own. So this notebook should be pretty self-explanatory. I'm just going to walk you through the commands and show you. So if you don't remember how to get to or how to open an empty notebook, go to the plus sign, click on that button. You see these icons here. We're going to open up a Python 3 notebook. Double click there, and we have a new notebook. So the first thing we need to do with Python is built in packages. So we need to import those packages into Python in order to be able to use them. And we can do that. There's a number of different kind of syntaxes to do it, and hopefully there's a good array here of how we do it, but we're just going to use a simple import of Earth Access. So we type import Earth Access, and that imports the whole of the Earth Access library. We're also going to use Xarray in this example, and I'm going to import Xarray, but I don't want to have to keep typing Xarray, so I'm going to rename it as XR. That's a pretty common short name for Xarray. Then in order to plot the data, which is what I want to do right at the end of the demonstration, we're going to use hvplot, and that has a plugin to Xarray. And it's a really nice tool, especially for working with big data sets like ICESat-2. So we're going to import HV plot, but this time we just want to import the X-array, or the part that works with X-array from HV plot. So we import HV plot dot X-array. And then finally, just for pretty printing, I'm going to import pprint. And you can run that cell just by clicking on the arrow, the play button here, or you can use shift return or shift enter, depending on how you refer to the return button. And hope you should get no errors. We just see all those libraries, those packages have all been imported. So the next step is we want to authenticate in order to be able to use Earth Access. So we're going to use the Earth Access login, and we just type earthaccess.login. Now, you should all have Earth Data Login usernames and passwords. If you're all new to CryoCloud, you probably don't have a NetRC or environment variable set up. So you will actually need to enter those in this step. So it will automatically prompt you for those. It's not going to prompt me because I have a NetRC file which kind of automatically logs me in. So what you should be seeing is a prompt for Earth Data _username. And just go ahead, enter your username, enter your Earth Data password, and that should get you through that step. Now, if you want to actually preserve those, you can type in earthaccess.login and then give keywords strategy, interactive, and persist true. I'll just type that here, but and that should create a NetRC file for you. But just typing in your username and password will work. Does everyone have, that will create an NetRC file for you online? Yeah. If well, let's see what happens. No, it tells me that I'm already authenticated. But you could, if you wanted to, you could restart your kernel and run the two cells.
We will add to that. The NetRC file is really nice and convenient. It does provide people who could get into your system an easy way to access your username and password if that is ever a worry for you. So security wise, it is better to technically type it in every time, but ease of use. I just wanted to add that security point.
One question for that, because I tried to use an NRC file in the past with the token that you can get on Earth Data, right? When you go directly to Earth Data Login, create a token, and from some description that I found somewhere, I understood I could use that instead of the password, so you don't have the problem of someone accessing your password because those tokens expire after 3 months or something.
Yes.
But I never get it to work. So
okay.
Then in the end, I actually bought it. First access didn't work with the token and then I'm going to repeat the question.
Yes. So the problem is, and Luis is actually online, so he might suddenly pop up and answer the question in the Zoom. But the question was, you've tried using the token instead of the Earth Data login password, and that hasn't worked on Earth Access. Luis is definitely aware of needing for token, and it might already be in Earth Access now, so it might be worth retrying, and if not, we can work to sort that out.
Luis can chime in the chat. He says eventually we should use bearer tokens everywhere, but NASA doesn't support them everywhere yet.
Okay.
Yeah, it's kind of, I will, hear about it on.
Okay, so is everyone managed to log in? Raise your hand if you're all good. Okay. Anyone still working, waiting? Okay, I'll move on. Right. So so let's just do a simple query, and we're gonna search for ICESat-2 data. And we're going to use Earth access, and we're going to search for data sets, right? Also known as collections. So we'll use Earth access search data sets, and then we're just going to search for a keyword term. And so we'll look for data sets that include the keyword ICESat-2. Go, hypo. And that takes a little while, but that should return. There's 87 data sets. So it's that query has found 87 data sets that actually have the keyword ICESat-2 in them. And this is querying the Common Metadata Repository, CMR. We can I don't know, you can try it. Let's try it. I don't think it is, but yeah, it's not. Yeah. That might not return as many, but it might just.
I was gonna ask if the keyword search.
Yeah. So
they were like standardized on what the keywords are.
No, I mean, I think it's just like it's like doing a find in a document, right? If the spelling's the same and you don't use any wildcards, then it's going to be so. Now, all the information that what's returned from CMR is included in the query. We can take a look at that just using a simple Python idiom. So I'm gonna just print the first 10 returns, or the first 10 results that we get back. I'm going to use pprint just to make things pretty and more readable. And we're going to read or print the collection summary data. And we want to sort information so it all looks the same. So I'm going to use sort dix as true, and then so that we get it nicely indented, I'm going to indent each part of each dictionary by 4 spaces, and then we'll just separate those by a line. And you can see we now get a bunch of information that's returned.
For scrolling, is that what you're trying to do?
Yeah.
So just
Right. Okay. I'm holding it down rather than okay. Yeah.
2 fingers.
Right. Not used to a Mac. Right. Okay. So you can see here that we get a bunch of useful data here. We get the concept ID. That's how most DACs have a unique identifier for their data sets. We get some information about the file type. We get information, well, you get links for where to get the data. We get the short name, which is also another way of identifying it. The top one here is ATL03, and we get information about the version. So this is version 5 of ATL03. That's the first result that's been returned. If you look at the second element here, you can see that we have cloud info, and that's because this data unlike the first one, is located in the cloud. It tells you what region it's located in. That's US West 2. It gives you the S3 buckets. That's kind of the file system is S3, and data is stored in buckets. So it gives you the bucket name that information is stored in, and it also tells you how to get credentials. You don't really have to worry about that because the Earth Access deals with it, and then it gives all the other information there. So I'm going to close down that result, and this is something with notebooks. If you click outside of the cell, you see these two blue lines. You can collapse the results just by clicking on that blue line. You get 3 dots. Now, if we want to just get cloud data, we can pass the cloud hosted keyword to that. Do exactly the same search. But this time we're going to tell it cloud hosted equals true. And now there are only 39 data sets, ICESat-2 data sets that are hosted in the cloud. Now, I know that I want to look for ATL06 data, and I want to do a search for granules within a certain region. In this case, it's the region, the southern end of the Juneau ice field in Alaska, and I want to search for it over a particular date range. So we're going to use, in this case, we're going to use Earth Access search data. And this time, so we did search data sets to look for data sets that we can use. We know the data set we want to use, so we're just going to search for data granules. And we're going to search by short name. And we should have all the short names for the ICESat-2 products burned in on our brains and retinas by this time. We want the most recent version of that data, version 6. We want to make sure that it's in the cloud. So we set cloud hosted to true. And then we're going to set a bounding box. And in this case, we're setting a bounding box. You can also search by polygon. You can pass shape files into this. So it allows for all different kind of spatial search methods. I know what the bounding box region is. It's at -134.7 degrees, 58.9 degrees latitude, -133.9 longitude, and 59.2 latitude. It really doesn't matter what you put in here, because as long as you're between -180 and +180 and just -90 and +90, you'll get some data, right? Well, but so the bounding box is the minimum latitude, the minimum longitude, the minimum latitude, the maximum longitude and maximum latitude. And then we're going to search for do a temporal search. Temporal, right? Yeah, there we go. Bring me up, right? And we're going to search for March 2020.
Lisa's just adding that you can search for multiple collections at once, so you can have basically a list that would have like ATL03, ATL06, whatever data products you want before.
Great, thanks, Luis. And yeah, so Luis has just pointed out that if you wanted to search for multiple products, say you want to ATL03 and ATL06, you could just pass a list. I'll just type this in to demonstrate that, but so you pass it a list like that. Right, so we'll set this off. Right. So it has found 2 results for data, ATL06 data hosted in the cloud. And having looked at the data sets, know that those are the 2 latest versions, as version 5 and version 6. Well, 2 granules. And we can list those granules, and you can use a really useful little IPython tool called display. And this just displays those results. Yes. Thank you. And you see that we see a couple of granules there that have been returned. I guess I must have. Right. Yeah. So we've got 2 granules that fall within that region. I think the original notebook returned 4, but we'll go with 2. And you can see we see the actual file name for that granule. We see the size of the granule. We know it's in the cloud. And then we get these 2 little thumbnails of showing the data and also a map with the location of that data on there, which is actually quite useful, just to make sure you're getting back what you want to get back. Right. So let's load this data. And I'm going to use a magic command here, %time, which measures how long it takes to run the code that's in this cell. And because we're looking for cloud data, we have to do this extra step, which is to open the files that are in results. And the reason we have to do that is that the file system in the cloud is different to the file systems we have on our local machines. And most of the tools we have to read HDF5, which is the format that most ICESat-2 data is stored in, those tools need to work, have been designed to work on a local file system, right? Our local file systems. So what this earthaccess.open method does is to create a virtual file system on our computer that allows us to read the files that are hosted in the cloud on the S3 bucket, just using the normal tools. So you can think of this process as pretty similar to you just accessing a file on your hard drive. But because we're in the cloud, because the computing instance that we're using for CryoCloud is in US West 2, and the data is stored in US West 2, we can access that directly. So we're not having to download, right? We're just reading the data into memory on this compute instance, which saves you a lot of time. And then we've opened those files, and we're just going to read one of them, the second one, because that has the most interesting data, using X-ray. And Python lists 0 indexed. So the second one is index 1. And then we're just going to read one group. HDF5 files are organized into groups. We're going to read Landai segments for the 1L, the pair left beam of the first pair of this ground track. And we just do that by typing the path to that group in here. So earthaccess.open is actually opening both those files, but then we read just one of them into a X-ray data set.
So can you scroll back up to
The
query?
oh yes, yeah,
Search data.
yeah. Am I good? Can I make it? Yeah, I can probably do that.
Oh, Luis just has a comment on the query. It says that the CMR can be a bit slow these days, but can run queries and you get lots of
representation mode in the view. View. Oh, in view in the Jupyter notebook. Oh, right. Okay. Yeah.
Comment and plus. Comment.
Yeah,
and
I
plus.
tried that. That was not working. Oh, command plus. Oh, yes. Sorry. Yeah, you're right. Yeah. Okay. Is that better for everyone? I apologize for having that too small. And we can close that so we can go even bigger.
Okay, it's not working fast.
You good, Ben? What's the question? What's the problem?
I'm getting data granules dot bounding box missing 3 required.
Oh, I had square brackets, you do it for the round bracket.
Oh yes, it's a tuple. Yeah,
Got
yeah,
it.
yeah.
Really tough people.
Yes. Yeah, we haven't built that option in for. Okay, so that finished, and I'll quickly just I'm just gonna scroll, make that a little smaller. So we've now got that group loaded into an X-ray data set. We have delta time, we have latitude, longitude as coordinates, and then we have the 5 data variables that are there. We have the quality, we have the land ice height, and we have the standard deviation, and then segment ID and the height above the geoid. Let's plot that just so we can see. And we're just going to plot the land ice height. And I'm going to plot it as a scatter plot. And with the interactive plots is that if you get your cursor in the wrong place, you end up zooming. But one of the nice things with using HV plot is that you can do things like this and zoom into the point cloud. And that's this is a useful workflow, right? You don't have to download data to your own area on CryoCloud. You can just work with that information in memory, which is quicker, safe storage, and it makes it a lot more reproducible because people don't have to worry about storage requirements, and you can just run through this. And Earth Access allows you to both query data, search for granules. If you want to make sure that you're using the latest version, CMR is always going to have the latest version on there, so you can choose the highest version that's available and make sure that you're always up to date. If you want to make it completely reproducible, then you can hard code that version in there. So that's all I have for that. I'll pop back up again to show a more detailed example later. But okay, thank you.
All
Are there
right.
any questions?
Any questions for Andy? Cool. All right. So for the next tutorial, we're gonna have Wilson Satoff giving us a walkthrough. We will be transitioning, go back to our book directory. You can go to tutorials. And then go into the ICESat-2 ATL15 directory. And this will get us to where we're started.
Cool, thanks, Tasha.
All right, great. Was everyone able to navigate to that new folder, or do people need a minute? Alrighty, I think everyone's gotten to the folder. If not, speak up. Go ahead and open the one IPython notebook that's in there. And you can tell it's a notebook because it's got that orange logo on the left-hand side of the file name. Cool, great. So this notebook's entitled ICESat-2 ATL15. This is the gridded Arctic and Antarctic land ice product to investigate ice surface height anomalies. So I wrote this with Luis, who's online, Jessica Scheik, and Tasha Snow. The part that Luis wrote is the Earth access bit that Andy just kind of walked us through. So we won't do that latter part of this notebook, but we'll do the first part. So here are some of the things that we'll take away today. We'll learn how to grab data from disparate sources. We'll learn a little bit about a coordinate reference system, why it matters. And then we'll use geometries like points and polygons to find a region of interest and subset data. And then we'll get the basics of how to use ice picks to simplify obtaining and interacting with ICESat-2 data. And we'll use X-ray to simplify the import of multidimensional data. And then lastly, we'll open plot and explore gridded raster data. Oh, sure. Yeah, so if you ever need a bit more space to interact with your notebook, if you've got a lot of written stuff or longer code lines, you can just toggle your File Explorer open and close to have a bit more space, or perhaps you had two windows open. Okay, great. So first thing we want to do is set up that computing environment. Tasha kind of mentioned before, if you had a library that you were utilizing that wasn't part of the Jupyter Hub image, you'd have to do a %pip install. And so that's the case for this notebook. We need this open PyXL to read an Excel file. So we'll just pip install that. Okay, looks like that worked successfully. And then from there, we can just do our imports of different libraries. And we'll define a utility function that converts longitude, latitude coordinates into polar stereographic coordinates. Okay, great. So just a really quick introduction on Greenland subglacial lakes. This is a figure from a recent review paper by Livingstone and others. So this plots out the geographic distribution of subglacial lakes in Greenland and the Canadian Arctic, and some of the ice caps on Devon and Iceland. You can see there's two types of lakes. There's the stable volume lakes that have been observed to be stable in their volume over the observational record. Those are in the red dots. And then we've got active subglacial lakes in the blue triangles. So those ones will actively fill and drain episodically. And so we can see those when the ice surface deforms above those fillings and drainings, as the ice will uplift and subside as the lake drains and fills. Okay, great. So we can actually grab all the data from this paper because they've got an associated data set in their paper. And what I have done is I've downloaded that Excel file and then I've uploaded it to the CryoCloud books. It's already in here. It's this file here. And if we want, we could kind of, let's see, should be able to open this in CryoCloud. Let's see. Perhaps not. Okay, that's a no. but we can open it with Python. So we'll go ahead and do that. Reload this file. Oh, gotcha. Okay. Let's see if we can load it into Python. 1 second. Okay, so this would be an example of some data set that's not cloud hosted. You know, it's just an Excel file. It might be something that we get from a collaborator, or we downloaded from supplementary materials on a paper. So this is an example of that. So like I said, I downloaded it and then uploaded it to CryoCloud, and now you all have it because you cloned the repo. So from here, I was able to go into the Excel files, you know, using Excel, and then I was able to kind of look at the file structure and know that I wanted to look at the Greenland sheet, because this tutorial was created for the FOGS meeting, the Future of Greenland Ice Sheet Science. So we wanted to have something that was of interest for those users. And then we're only interested here in just a few of the columns. We want to know the name of the lake. We want its latitude and longitude coordinates and the lake type and the reference that's associated with it. So we're just going to pull in those specific columns on this specific Greenland sheet. So that's what this code block is doing here. And you can see that worked successfully. The files in there uploaded already. And what I've done is I'm just looking at the head of this data frame. So I'm looking at the first 5 entries here. And so you can see we've got that in. But because I grabbed this from a supplementary materials on a paper, it has a URL associated with it. So that means that I could bypass this step of downloading it and then uploading it to CryoCloud, and I can read it directly from the URL. So that's what this next example does here. Doing kind of the same thing, telling it that I want specific columns, telling it that I only want to read the Greenland sheet, and then opening it up in a pandas data frame. So we'll do that again, but again, instead of using the file that's in this file explorer, we're instead using this URL. So basically, we'll do the same thing, give us this pandas data frame, but it simplifies that step of downloading and the uploading data. So it can kind of simplify the workflow there. And then from there, we'll convert this pandas data frame into a GeoPandas geodata frame. So GeoPandas geodata frames have a bit more functionality in that they have a column, the geometry column, that can allow you to add points or polygons or line strings or multi-polygons, so something that's associated with that line of data. So we'll do that here. We're essentially just taking our data frame, and then we're creating this new column called geometry, and we're taking the points that are in the longitude and latitude columns to create this new GeoPandas geodata frame. So we'll do that here. And you can see we've got all the same columns, but now we've got a new column that has created a point object of the longitude latitude. Cool. And then from there, we can kind of filter on our data to look at the ones that we could look at with ice surface height anomalies with the ICESat-2 data. So we'll just filter this GeoPandas geodata frame by the lake type and just look for the active ones. So what this cell does here. And then as you can see, we've got 7 of them that are in this recent review paper. And then from there, this is a brief intro on what is a coordinate reference system. So this tells you how the Earth's 3D surface is projected on a 2D plane. And you can see here these different projections of the contiguous United States on 4 different CRSs. And you can see it will distort the landmass in different ways. And so we really do want to select a CRS that's appropriate for our region of interest. And yeah, there's a bit more information and some links here if you want to read up on this. And I enjoyed this figure. It was very intuitive of, you know, how it would distort land masses on a human head, which is roughly, you know, it's the spherical. And then these height changes that we'll be working with, they're all referenced to a datum. So there is some information here about datums. If you wanted to learn more about that, but we'll kind of power through and move on. Okay, so this next step, what this will do is it will plot up a, it'll use this data set that's built into GeoPandas data frame, which is just the kind of like the continental land masses in low resolution, so that we can look at Greenland plotted in different CRSs, along with those active subglacial lakes that we're starting to investigate now. So you can see here on the left, this is WGS 84, the World Geodetic System 1984. This is a very common one to plot the entire globe. But you can see what it does is it really distorts high latitude areas. You can kind of see the landmass has been exaggerated as you get towards the North Pole. Whereas if we used a coordinate reference system that's specific to the Greenland area, this 3413, it does a much better job of not distorting the landmass. So we get something that looks a bit more realistic. So yeah, you can see the differences there. And then we've got our 7 active subglacial lakes plotted to see where those are. Okay, great. And then what we can do is use a Shapley polygon geometry to create a search radius around those points that are the active subglacial lakes so that we can start to query for ICESat-2 data. So that's what this next cell does. What we are doing here is creating a geoseries. You can think of a geoseries as just like a column that would be part of a GeoPandas geodata frame. And so what it's doing is it's using our GeoPanda geodata frame. We're converting to the CRS that's specific to Greenland, and then we're creating a buffer around those lake points that is 10,000 meters or 10 kilometers around that lake point. So we're just making a circle around that polygon so that we'll use that as our area of interest to investigate a little bit further. And then I'm just going to make a copy of this GeoPandas geodata frame. So I'm not altering the original GeoPandas geodata frame. I'm just kind of starting with something new so I can make alterations and whatnot. And then I will look at that GeoPandas geodata frame just to make sure it did everything that I was expecting it to. And it looks like it worked. You know, kind of got that original, the data frame contents, the name, long lat, lake type, reference. But then in the geometry column, instead of just having that point that was in that original supplementary Excel file from the review paper, I've instead made a polygon around that point. And so I'll use that as my search radius to search for ICESat-2 data. So I think I can skip this next section of what is ICESat-2 data. I think everyone here is pretty familiar. This is just kind of a walkthrough of what the instrument does, and then a little bit about the ATL 1415 data product. So the ATL 15 is a gridded raster product of the ICESat-2 point data. And it gives us height changes in 3-month intervals, the repeat orbit time of ICESat-2. And so we can look at height change patterns from one repeat orbit to the next. And then ATL-14 is this accompanying high resolution, it's a 100-meter digital elevation model that is this spatially continuous gridded data of the ice sheet surface at one reference time point. So they're kind of paired in that way, in that they're both rasters, but one is just a surface, and then the other one is changes relative to that surface. Okay, cool. So this next step, what we'll do is we'll stream cloud-hosted data from NASA Earth Data Cloud. And I've got a few links in here that can kind of walk you through a guide of using that kind of data if you want to learn a bit more. But what we'll do is we'll use this library called IcePix that can simplify this process for us and allow us to authenticate with AWS, similar to the Earth Access library, the way that happened. So what we'll do here is IcePix uses files as its way to search. So it can use like KML files, it can use geo packages, but it basically uses a geographic area to search for data. And so what we'll do is we'll just search for one of these lakes, and we'll just create this geo package file that will allow us to search for the area around that specific lake. So that's what this cell is doing here. And then from here, we create these query arguments. We're going to search for our data product using the short name. We'll indicate the spatial extent using that geo package that we just created in the last cell. And then we'll give it a date range of the dates that we're interested in. And then from there, we create this region object, and then run that off of IcePix. So this is the alias for IcePix, IPX, and then the query method off of that. And then you feed it in the short name for the product name, spatial extent, and date range. And so that is what that's doing. And then from there, we can visualize the spatial extent of that region object using this visualize spatial extent method off of it. And you can see it's using that HoloViews data visualization package. And you can see it's an interactive. We can zoom in and out on this one and see if we got it right, if we're in the right spot. And it looks like that's right. We were interested in this particular lake that's on this ice cap that's in the northeast corner of Greenland. So that's looking right there. And then from there, we can search and see what data granules are available from that region. So it looks like we've got 4 data granules, and that's because there are 4 resolutions available for the ATL-15 product. Because subglacial lakes, the active ones are really small, we want to use the finest resolution one, which is the 1 kilometer. And you can see that here we've got ATL-15, GL for Greenland, and then you've got the different kilometer resolutions. So we'll just use that 1 kilometer resolution, the highest one available. And you can see what we're seeing is the names of these files, and then we're getting the S3 bucket URLs. And so from there, what we'll do is we'll store the S3 URL by just calling off of the granule IDs and then indexing to be this last one, the finest resolution one. Oh, whoops. Cool. Okay, there we go. And just confirming that we stored that properly. Yes, it's the finest resolution. Very good. And then from there, we'll again use this region object and use a method off of it, the Earth data login method, and then tell it that we're looking for an S3 token, and that will allow us to sign in. And then, yeah, similar to Andy, I do have a netrc file in my file folder, but if you're running this for the first time, it'll probably ask for your username and password. So I'll give people just a minute to do that if you are working along interactively to fill in your username and password. People ready to go? Cool. Excellent. So next up, we'll be storing these S3 login credentials so that we can access the cloud-hosted version of this data set. So that's what this file does here. And then from there, we'll use these stored credentials in this S3 object to open our S3 URL and then read it into an Xarray data set using Xarray.open data set. And we're going to look at the delta H group of that particular data set. So that's what we'll do here. And we'll see if that worked out for us. Cool. So that works. So this is kind of a preview of what an Xarray data set looks like. We've got the coordinates that kind of bound all the data variables in the data set. So this one's got X, Y, and then a time variable for all the quarterly height changes. And then we've got our data variables. So we're interested in this DH variable, but then there's other things like the sigma and delta H and the data count and other things that we might be interested in. And then we've got sometimes attributes that get read in that can tell us a bit more about the data set. And we can also get these kind of previews of the data if we click on this this little icon here. It tells you, what it is, like if it's an array. Sometimes it'll preview the values like this one. And then from there, we can also click on this little note icon to just get some metadata about those data variables. So that can be one way to get acquainted with the data set. Some other ways that we can acquaint ourselves with the data set is we can look at the DAX overview page of the data product. So this is the one for ATL 1415 here. So it gives you some very basic information about the data format, its temporal and spatial resolution, its spatial coverage, those kind of things, and then all the different access avenues there. We can also use that Xarray dataset read-in to look at the metadata that gets pulled in. That's another way. There is also data dictionary associated with this. So if we don't know a specific thing, this is a very long document. So this is a great way. This is one to do, Control F or Command F, where we might look for a particular variable just to kind of read what it is. So we're looking at this one. It's telling us it's a float, the quarterly height change. So that's what we'll be looking at. So that's a way to learn a bit more. And if you really want to get into the weeds, there is the algorithm theoretical basis document that you can read a bit more. And for one of these higher level data products, it could be worthwhile for you to learn a little bit more about how the data product is created. Okay, cool. And then from there, yeah, good point. I should add a bullet point for that, for those. Great point. Thanks, Tyler. Okay.
That's right. And bring one.
Okay, cool. So there's a couple ways that we could look at height differences. We could subtract out the datum, so the ATL 14 directly. And remember, ATL 14 is that complementary data set. Or if we're looking at height changes from one quarter to a next, if we're doing that, we basically subtract out the datum, and you can see that with this equation here, where the datum just kind of disappears, and we're just looking at height changes from one time step to a next. So that's what we'll do here. So we just are going to be using ATL 15, and this code chunk here will plot up the height change from the second repeat cycle from the first. So we'll see what that looks like. Okay, cool. So we can see there's like a little bit of change at the margins. We've got some blues here, but we don't see much going on in the interior. And you can see that that is really driven by the fact that we've got some pretty extreme values at the margins. Our height change color bar here is automatically going from plus 10 meters to minus 10 meters. Yeah, Ben.
The extent is not going to be right. You're using the latitude longitude extent and the ATL 15s and forest area.
Oh, I see what you're saying. Let's see.
So you want to use the X and Y variables and stretch between, get it approximately right if you use the first and last value. I was wondering, I was stretching that why.
Yeah, why it's so stretched. Okay. Yeah, I did not think about that, but that's totally right. Yeah, thank you for pointing that out.
If you try to interpret a latitude and longitude off of that map, it will not be right, because it should be distorted. Like it should also have the fuller stated it should look more mushroom shaped than this. It's just squash, but it should also be mushroom shaped that we're using latitude coordinates.
Right. Yeah, great point. I'll have to go through and fix that. Thank you. Appreciate that. Yeah, for folks online, what this is doing is it's plotting in longitude, latitude coordinates. You can see that here, but you can see it's using the extent from the data set, which are this, min X and max X values. But whereas if we go back to the X-array data set, you can see it's not in longitude, latitude, it's in polar stereographic X and Y. So that's why it looks a bit wonky and stretched. So I'll have to go through and get that fixed. Cool. Okay, so yeah, like we said, we're not seeing many height change values in the interior of the continent. And we talked about how that's because we've got these really extreme values along the margins. So what we can do is we can use methods off of this height change difference. So we did, the second cycle minus the first cycle, and this gave us our DHDT data array here. And what we can do is we can look at what the min and max values are. And so you can see it's a plus 10 and a minus 3. And so this particular data visualization package, the hollow views, it's going to pick the maximum in one direction and just plot both. So that's why we're seeing some of the blue values, but not any of the red values. So we can adjust that same code block and use this matplotlib colors to slope thing here, where we can actually tell it, what we want to plot for the minimum and maximum for a color bar, and then we can see a bit more of the data structure. So you can see here, it's still at the +10, but then we've got a negative value that's more around 3. And so now we're starting to see some reds along the margins, but still we're not seeing much data structure in the interior of the continent because of these extreme values out in the margins. So we can use a method off of the X-ray data array to look at quantiles. So we'll look at the 1st% and the 99th percent quantiles of the X-ray data array. And so yeah, there's lots of little methods that you can do off X-ray data arrays and data sets to get some valuable information. And then from there, what I can do is just put that into that 2-slope piece of code here so that I can see a bit more of the data structure in the interior of the continent. So now we've got some data bounds, and I changed the shape of this color bar to be pointy to just kind of indicate we've got some extreme values that are being plotted as that are kind of beyond the color bounds. And so we can see a bit more there. Okay, cool. Okay, great. Another way we can sort of automate this and do it for like all of our time slices is just by writing a function. So that's what I've done here. It's essentially what was in those last few code blocks, but it adds a few things to kind of clean up the axes and do a few other things to make it look a little bit nicer. So you can go through that if you are interested. So I've created the function there. And then I'll just remind myself, the different active subglacial lakes, so we can look at one of them using that function. Okay, great. So I'll just pick one of them. Instead of looking at this ice cap one, we'll look at the next one down. So I'm doing that here. I'm subsetting this GeoPandas geodata frame. And then from there, I will go ahead and call that function. And this sets up the latitude and longitude bounds and then translates that into an X and Y. So we'll plot that specific lake. And then this function will create a trellis plot that goes through the different time cycles. And you can see we're going through here. Don't see anything that looks particularly lake-like, but a lot of these active subglacial lakes are kind of like close to the margin. So it looks like we are getting some pretty strong seasonal cycle of, melt and then accumulation. So that looks like that's what's going on here. But you can go through, use that function at the different lakes if you wanted to look at the other ones. And then another thing that we can do here is we can use hollow views to do an interactive plotting using X-ray. So what this will do is it'll take the X-ray data set and look at that data H data variable. And then we'll be grouping by the time, and we'll give it a color map and a few other arguments here. And what this will do is it'll create this hollow views visualization that you can actually interactively play through. So it'll actually play through all the time slices, and you can see it shows the time information there, and it's adjusting the color ramp for each particular difference between cycles. So it's a useful way to do some initial data exploration. Okay, and then we created this intermediary file, this geo package, to be able to search using IcePic's area of interest and grab the data granules that were associated with it, but we no longer need it. It was intermediary. So this cell just removes that geo package data frame. And then the rest of this notebook kind of runs you through how to access data using Earth access, but we've already gotten that tutorial from Andy. So I will open it up to questions if anyone has any of those, including online folks. And if there's nothing, I'll turn it back over to Tasha.
All right. Thanks, Wilson. How's everyone doing? Do we need a 5-minute break, or I think we have about half hour left of tutorials, and then we'll get to our own code and going through anything extra, having any other questions that you guys have. We'll be able to open up your code if you want to after that, but we have about 30 minutes left of structured tutorial. Do y'all want to break or push through? Thumbs up for push through. All right, let's take a 5-minute break. Sweet. Thank you. All right, let's get started. The next tutorial is going to be run by Andy again. We'll start by moving over to the CryoCloud book back to the external directory there. And we're gonna this time pick the ICESat-2 ATL10 H5 Coro tutorial. And I'll turn it over to Andy.
Right, great.
This stupid thing.
I can, yeah. Okay, so we, NSIDC have been kind of doing these tutorials both for NSIDC and also for the NASA OpenScapes group for some time. We got to the point where we're like, we are demonstrating what is generally toy examples, right? We want you to learn, we want you to kind of have small snippets that are hopefully easy to understand and implement for you. But we've been realizing that really, if we're going to demonstrate the power of cloud, then we need to scale up and start doing something kind of workflows that you will be doing in your everyday work life. I'm not sure that this necessarily goes all the way there, but this is the bare bones that should allow you to scale up. So what I'm going to be showing you is essentially trying to recreate the ATL20 gridded sea ice freeboard product. And that uses information from ATL10, which is the along track freeboards. I'm just going to focus on the Ross Sea region for the time being, but you can scale it up to Antarctica. We're just doing it for a single month, September 2020. At the NSIDC DAC user working group last week, Alec Petty ran this for 3 years worth of data, and it took a really short time to run. So this hopefully has the ability for you to scale up and use it, whether you're using it to try and regrid ATL06 or whatever other data set you want to work with if sea ice is not float your boat. So I'm gonna run through this. I'm not going to be live coding because there's a lot of stuff in here that I just will take me ages to type, and you don't want to see me make that many typos. So the first thing to do is we need to install some versions of libraries that are not in the CryoCloud environment yet. And we're going to be using that pip install approach that you saw Wilson use just a moment ago, and Tasha spoke about. I've been using the old style of using an explanation point to do pip, but I'm going to change these in here so that they use the pip magic. We're going to be using a new version of Earth Access, which allows us to take advantage of some of the new features that have been implemented in a package called H5 Coro. Now, you've probably heard a lot about slide rule this week. H5 Coro is a cloud reader for one-dimensional HDF5 files in the cloud, and it was developed by JP Swinsky and the slide rule team, which Tyler and Ben are part, to allow performant access of cloud hosted data. And we've done some testing with H5 Coro. We did it at the ICESat-2 Hack Week. And it is just way faster than using standard HDF5 readers. So we're going to be using H5 Coro as well. And we had to make some changes to Earth Access to make that work. So I'm also using this capture magic command at the top here. I know this install works. But what it does is to create a whole stream of output as it's installing these libraries. So capture just captures all that output and prevents it from appearing on the screen. I also want to draw your attention to kind of, well, I guess three things, but two things in particular. One, we want to first of all uninstall Earth Access in H5 Coro because we want to put new versions in and we don't want the old versions hanging around. But I want to be very specific about, and I'll highlight this because those of you online can't see what I'm pointing to on the screen very well. So I want to be very specific about the version of Earth Access. So pip and conda allow us to specify the version. We're using version 6.1. And then here at the bottom, you'll see that this is a little different. This is a little different. We're actually, this version of H5 Coro is under development. We know it works, but it's not yet in the PyPy, which is the Python package manager. So we're going to install that code directly from the GitHub repo. Everything's there, so it works nicely as a package. It's just not available by the normal routes, so we have to go to GitHub. So these are two kind of key things to remember, especially as you're kind of getting towards using cutting edge kind of versions of tools, that you can install stuff from your own repos or other people's repos to get them working as packages on the machine. So, and then we're going to install a bunch of other packages. The import for OS and setting this use PyGeos equals 0 is to force GeoPandas to use Shapely instead of a package called PyGeos. Otherwise, it throws a warning, and I got tired of seeing the warning, and it tells me to do this if I don't want to see it, so I just followed along. We're going to use Earth Access. I'm going to be using NumPy. I'm going to be using a few features from Pandas, this utility called datetime, and then I'm going to be doing some resampling to a grid, and affine and affine matrices are really useful for doing that kind of resampling work. So I'm going to be using this affine object from that library, and then usual suspects, matplotlib and cartopy for doing the plotting. And then we've written some helper functions from that we originally put in a directory called H5 Cloud in this module called read ATL10. In actual fact, if you look in your directory structure here, you'll see that read ATL10 actually is sitting in the current directory. So I'm going to ask you, before we do this install, well, I'll run it and show you how it fails first, and then we will correct it. So it's telling me that it can't find a module named H5 Cloud. And I realized, as I said, read ATL10 is actually in our directory structure. So I just need to, in this case, change the path to just look directly for read ATL10 rather than this directory called H5 Cloud. So if you want to go ahead and just delete that H5 Cloud from that line, it should work. And it's telling us that the version of Earth Access that we're using is 6.1. Then we're going to do this authentication step next. And I'm going to, if you need to type your credentials in again, go ahead and do that. I'll just wait for a while, for a moment while you do that. You should be pretty good. everybody got lucky with typing their credentials in. So, and this is kind of just setting a few parameters. I want to look at the Ross Sea region. I have put in a bounding box for Antarctica as well, but all this section is saying is, you know, if this region or the region argument is Antarctica, use this bounding box. Otherwise, use the Ross Sea bounding box. I want to restrict it to Ross Sea. And then I'm setting the year that we begin and the year end. They're the same because we're just looking at September of that year. So I'll set those. And then this is the search part. And we're doing there's a lot going on here because we wanted to allow it to be expanded to multiple years. So we do a granular search for each year. I set the dates that I want to search for, and I'm formatting them as a string, so it comes out in year, month, day format. And then we do that search for 1 year. The results get fed into a Python dictionary that we're calling ATL10 here, that is indexed by that year. And it goes through however many years you decide you want to run it for. And then we're going to print out some information about how much data we've actually pulled as a result of that. It's just going to run through once because we're only using 1 year. And it finds 59 granules. Just going to shrink this down a little bit so that I can see what's going on. Oop. There we go. So it's still running because it's even though we're getting results printed out, it takes a while. So that's 5 gig of data almost that we've downloaded there, 59 granules that cover that Ross Sea region. And then we want to read this data in. Right, and this I'm using this helper function read ATL10, but we're also got a couple of other helper functions here. We've got get data links, which all that does is to just change the links so that they point to the S3 bucket where the data is stored, because we're still working in the cloud. That little setting up of credentials that Wilson just showed, I've encapsulated that in a function just to make it a little easier. And then we use this function read ATL10, and I just want to show you a little bit about how this works, because it's important that you know, ICESat-2 files, you know, each product has a different file structure, and we want to get different data from different places. So sometimes you have to write kind of like bespoke functions to get the data. And because we're using H5 Coro to do this, we've had to do a few little changes here to make it work. So there are actually 2 functions nested inside of each other. And the reason we do that is so that we can parallelize the whole process. So read ATL10 takes in files. If we needed bounding box information, if we wanted to constrain that data down even more, we could do that. There's an executors variable that sets the number of threads we can use. So each processor can spin off processes in different threads, and that's how we parallelize it. We're using, we're only going to work on a single processor, but we can still have a number of threads working. We can set it if we want to work locally. We're going to be working in the cloud, and we feed in the credentials. So we set up the environment first, whether it's local or in the cloud, and we have to use different drivers. That's what this section here, this if environment section does. We then need to, because we need to convert the delta time variable, we set the GPS epoch, which is 6th of January 1980. That's when the GPS system started, or when the time stamp for that starts. And then what we're doing in this H5 Cryo reader, just shrink it down a little bit. So we initialize H5 Cryo. That's essentially a file object, and we're running this on each file, but we're running the files on separate threads. So we open a file object, we get some ancillary data sets. We need to know the orientation, because we're only using strong beams, and that is dependent on which way the ICESat-2 satellite is oriented. So we get that information from the file, and we need to get some more information about how many seconds to add to the delta time for the data in the file. So we grab that information that's held in the Atlas SDP GPS epoch. Wilson also talked about data dictionaries. So if you can find all this information in data dictionaries. And then H5 Cryo reads the data sets. And what this is doing is actually searching through the HDF5 file, looking at the file level metadata and where the bytes for these particular variables are held. And then we set up, we say, okay, we want these particular data sets. We want latitude, we want longitude, because we need to know where they are. We want to get delta time, because that's a useful coordinate to have. And in order to do this gridding, we need to know the segment length and the freeboard heights. And I've also said, well, I want to know segment distance, and I want to know the type of the segment, because maybe I want to do something with whether it's ice, whether it's a lead, or whether it's a specular lead. So I've left that data in there, but you can set up a number of data sets that you want to read just by feeding in these paths. And then we go through the process of finding where that data is within the file. And then we just loop through, because we want to use all the strong beams, we loop through reading that data and creating the data set. And what I do is I read it into a GeoPandas data frame, just as Wilson showed for some of the other data here. And I know we use X-ray a lot for reading data. I'm coming to the conclusion that oftentimes reading stuff into a GeoPandas data frame, just because it's in a long track data, allows you to do a little more, or some tasks a lot more efficiently. It's my preference, but it's worth checking out. And then we return all of that we concatenate all that information together and return it as a single big pandas data frame. And now I have to find the notebook that I was working in. There we go. Great. So let's run this. So this is opening up the file object. It's getting information about where the data is in each file, and it's stuffing it into a GeoPandas data frame. And this is 59 files. It's 5 gigabytes of data. And we're using this library called PDQM, which allows this multi-threading. So we're actually doing this in parallel in the cloud. And the progress bars tell you how much time you've got to go to get coffee or answer email or whatever. So you can see how far along, but you can see it's actually going through pretty fast, right? I have tried this for the whole of Antarctica. It does take obviously a little longer, but it's still pretty fast. And I'm timing. I'm using the time magic command to get that. So we're halfway through. Any questions? Any questions online?
Not yet.
They've obviously realized they've got 30% of however long it's going to take to go get coffee. Okay. So
it says this is one of the coolest things about H5 Cryo. We can actually use threading and speed things up.
That's Luis.
Yeah.
Yes. Yeah. Okay. So 5 gig of data took 1.5 minutes to run through and generate a data frame. And I think what I didn't point out was I was doing that, creating the geometry column for the GeoPandas data frame as I'm going through each of those files. So this is our data frame, right? And I like to think of GeoPandas as you can basically do anything you would do in a GIS, but you're not having to pay a license fee to Esri. So I like that. You have to make your own maps. You don't have all the cool features that they add, but it's essentially a GIS at the command line. So now we're going to go into gridding that data. So we've got all this data. We've got the points in latitude and longitude. They are in the WGS 84 coordinate reference system. And Wilson was talking about that. I actually put some links in the Zoom chat for some resources that were put together by David Sheen during the ICESat-2 Hack Week about coordinate reference systems. And there's also a really great notebook that Tyler and several other people put together for one of the previous Hack Weeks that kind of really go into this in detail. And the reason I want to draw your attention to this is I'm setting this to WGS 84. That's a 2-dimensional coordinate reference system, right? And it's the coordinate reference system that the GPS system uses. But to be truly effective, we should be using ICESat-2 data with a 3D coordinate reference system, which is tied to a reference frame, which is, the plates on the Earth are moving. And so where you are in relationship to those plates is also changing. And so we have to update our coordinate reference systems and realize them frequently in order to make sure that we are where we are on the Earth. And it gets really complicated, as David Sheen points out in his help document, but we really need to be using, and I think it's 7139 is the EPSG code. At the moment, I'm using 4326, which is WGS 84, but we need to be aware of that. And I'm going to update this once I can get some more information in there. So we're gonna move on to gridding that track data. And so here, I want to put the ATL 20 data set is in the polar stereographic grid. What I want to show is that we don't have to, if we're working in the cloud and we have this computing power and we want to do our own gridding and stuff, we don't have to work in polar stereographic, right? We can work in the EaseGrid version 2, and in this case we're in the southern hemisphere, so south, or we can choose an Albers equal area projection and some other coordinate reference system, and we can choose the grid resolution that we want to work in. Most of our data is going into a 25-kilometer grid. I think it's a reasonable thing to do given the amount of data we have and being able to get enough data into grid cells. But I just want to say we can choose a 6.25 if we want, right? 6.25 kilometer grid. So that's what I'm doing here. I'm saying, right, let's set the coordinate reference system for the grid we want to use to be EaseGrid 2 south, and the EPSG code for that is 6932. And then I'm setting up the parameters for the grid that we want to use. And I'm just focusing a small grid over the Ross Sea region. There's an appendix to this notebook that shows you how I came up with the number of rows, number of columns, the width, and the upper left X and Y coordinates for that grid. But the reason I'm showing this here is that I want to make the point that the coordinate reference system is distinct from the grid we choose. I could create my own grid. There's an infinite number of grids that I can create for a particular coordinate reference system. In this case, I'm just creating my own that sits over the Ross Sea. And in order to do that, I need to know the shape of that grid, the dimensions, that's the number of row and columns. I need to know the resolution of the grid. I'm assuming that column width or pixel width and height are the same, 10 kilometers. And I want to, and I need to define the upper left X and Y of that grid. And then here, I'm just defining a map extent so that when I come to plot it, I don't have to type all that information in. I'm using these grid parameters to do that. Any questions on coordinate reference systems? Okay, so what I need to do in order to start the resampling is to go from the WGS-84 two-dimensional coordinate reference system to the EaseGrid2 South coordinate reference system. And GeoPandas has this 2CRS tool to allow us to do that reprojection. And so this takes a little while because it's actually got to go through like something like 15 million rows of data, but it does actually end up doing it pretty fast. And I'll use that time to talk a little bit. Oh, there you go, 16 seconds, didn't talk fast enough. But we're just going to use a drop in the bucket resampling scheme, right? So if a segment or the center point of a segment falls within a grid cell, I'm going to say it belongs to that particular grid cell. And then I'm going to create statistics for all the segments that fall within that particular grid cell. In order to work this out, there are some tools out there to do it. PyResample will do it, but this is it's actually a simple thing to do, and it's worth demonstrating. So this is just saying that in projected coordinates in that EASE-2 South coordinate system, there is a relationship between the column and the row position within your grid, described by these two equations here, right? X and Y are related to column and row with using those parameters of width, height, and the upper left corner of the upper left pixel. We can express that in matrix form, and this is the affine transformation, right? Or a reduced affine transformation. So it relates. So with this, what this matrix equation is saying, linear algebra equation is saying, is exactly the same thing as this equation up here. And we can encode that within this affine transformation using the affine class of the affine package. And all I need to feed in is the width, the upper left X, the height, and the upper left Y. At the moment, it doesn't know about the shape of the grid. We're just saying, I want to relate every point in projected coordinates to a column and row. And what we get out of that is a column and row expressed as a real number, because the spatial coordinate system of the grid is continuous, right? It's all real numbers. So imagine kind of having a map and laying a piece of gridded piece of paper over it and identifying where those points are, and the origin of that grid is in the upper left corner. Then you can count across the number of columns and rows where a particular point is, and that's what you're getting out of doing this affine transformation. So what I'm doing here is exactly that operation. I'm finding the coordinates in grid space of each point that we have in that GeoPandas data frame. And then I'm calculating a single unique number, the array index. Imagine I've unfolded that grid, so it's now a vector, and each cell in that vector has a unique index. And I'm just calculating what that unique index is for that vector, so I can put points into it. And I'm using the geometry information in the GeoPandas data frame, and we got an error. Oh, all right. And this is one of the problems with using notebooks, is that you need to make sure that your cells are run in order. And if you have a little thin cell, it becomes an orphan, and you need to repatriate it. So we're timing this. Doesn't take too long. I mean, it takes like a minute or so to do. But now we know which grid cells each of those segments falls in. Any questions? There's beer in the fridge. Anyone want to do a dance, tell a joke? Are there any questions online? So as I say, I'm using a drop in the bucket approach. And I've spoken with Alec, Alec Petty, who developed the ATL-20, and there's lots of other interpolation schemes. We could get pretty clever with how we do it. It's just this is the simplest and maybe kind of, we're not making any assumptions, but we could use bilinear interpolation. We could use some Gaussian basis function in order to do this. If we want to code it up, we'd have to change bits of this code, but the notebook allows you to play around with those things. And one of the things I was thinking of as we were talking about slide rule and seeing some of the things that people are doing, slide rule, people are working with the slide rule team to get their own processing streams into the cloud. But there's a step before that in that you need to really do some development work and figure things out. And this kind of notebook and this kind of workflow allows you to start doing some of that development work before you call up Tyler and JP and say, hey, can you do this for me? So now in my grid index, I've said that if any point falls outside of the extent of the grid, I'm going to code it as -1. And you can see here on the left, on the right here, let's get rid of this. You can see here that we've got a bunch of -1s for grid index. What I'm doing here in this step is to just get rid of those -1s. Then we calculate some cell mean statistics within ATL-20. They look at the mean segment length that fall within each grid cell. They calculate a mean freeboard weighted by segment length. So we're not biasing kind of lots of short segments and ignoring some of the longer segments. And then we create a standard deviation also weighted by segment length. And I just code those up into this, into these functions here. I'm still working with the GeoPandas data frame. And I want to use an apply method, which is part of GeoPandas. If you're familiar with pandas and GeoPandas, it essentially just applies a function to every row within the data frame. And so I wrap all these functions into a function that I imaginatively call allfuncs. And you can take a look at this, but testing your functions is a good idea. So these cells actually prove that what I did is doing what I think I did. So I have a test data frame that I've put the grid index, I've put the segment length, I've put some beam height information in. I've calculated what the expected values are for that in another data frame. I run the test run that test data frame on allfuncs to get a result. And then this PD testing assert frame equal is just saying, are my results, do they match what I expect? And I don't want to worry about using this assert frame equal means that I don't have to worry about a lot of decimal places, right? I can get it almost right. And that passes. If it didn't pass, it will raise an error. And then let's run it on all the data. So now we've got everything with unique IDs. We're calculating grid cell statistics for all the segments that fall within a particular pixel, and that's what this group by grid index argument is doing. So now what we've got to do is to take this list of grid cell statistics indexed by a unique identifier that relates to the grid cell they fall in, and just put all those values into a grid. And that's what this series to grid is doing. You can take a look at the function just to see exactly what I'm doing there. We'll run it, takes 4 seconds. And just to make sure that we're getting something that's sensible, let's just plot the image. I'm using ImShow here. And this is just a plot of the number of segments that actually went into each of those, each grid cell. But this is a representation, a raster of those grid cell statistics. Let's do something a little fancier here and plot that data. And when you're using maps, it needs to download some vector data, so it gives you a little warning. And those are the segment counts for each for all that data. So for the Ross Sea region, and this area here is ice shelf. So it's not included in the sea ice data set, but these are all sea ice values. Now we're probably more interested in the freeboard. So let's plot mean freeboard, and also let's make it a little more useful by adding a color bar to it with a label. Oh yeah, that's amazing. Normally I would just try and stuff a U in there and get a similar error, but there you go. So let's go up. And now we're seeing mean freeboard height. So that's essentially a workflow that you can use for trying to improve on some of the gridded data sets that are out there in the cloud. You're never having to download data to your local machine. Everything's done in memory, and we're able to parallelize the whole process. So hopefully it's a lot quicker than you would normally have. And there's many improvements that we could make to this, or you could make to this, using Dask and other libraries, and writing some of the code in a little more intelligent way than I've done it. So that's it. That's all I have. So thank you very much for your attention.
So I had a question on this. Andy, how long would this normally take without the cloud?
Well, downloading 5 gig of data, yeah. I mean, I think the largest time sink for this is just downloading data to your machine. And I was going to try that and give you a time, but I don't have that information. But I think, when I just, and you can try this yourself, if you just do a run all on all these cells, it's going to rip through pretty quickly. Like each of those steps were all kind of roughly, certainly less than 2 minutes each step where you had a lot of work. So the reading, the processing and everything, takes less than 10 minutes, maybe less than 5. So I think that's way shorter than trying to download all that data. And also having to worry about where do you store it and stuff. And you can share that around, right? I can send it to Alec, or I can send it to Tyler and say, hey, let's build on it. Well, what do you think? What stupid things have I done?
an H5 phone is so much faster than you would be able to do an S3 file or whatever. Where you
Yeah.
Yeah.
H5 files.
H5, yeah.
Yeah.
Yeah, H5, the one caveat with H5 Coro is that it only reads one-dimensional data at the moment. But
It should only be able to read ICESat-2 data
yes, yeah,
specifically, right?
uh-huh.
It's not any,
But the one dimensionality.
okay.
Yeah, I will say we've done some testing. If you want to, I get a presentation at the end so I can see that as a working group on benchmarking some different reading approaches. We had a project at the ICESat-2 Pack Week where we did that benchmarking work. One of the things we found is using a package called the Chunk, which kind of builds a lookup table for where the data is in the file. That actually, if you use that with X-ray, then that's a really performant way of reading data, almost as fast as using H5 Coro. And it's a lot more extensive generalized because you can read SDFRs, you can read multi-dimensional data. So that's also a good thing to check out. And what we're doing is this is where you need to read the track data,
Yeah.
the low level ICESat-2 products, but if you want to put things in.
So what Andy said was that the online group may not have heard was that CryoCloud is another way of reading in this data that is almost as performative as H5 Coro, but can be generalized to other kinds of data sets. So you can check out H5 Coro to do fast read-ins, because just using H5 Pi for this would be a lot slower to read in each data set segment. Any other questions or comments on this tutorial? Oh yeah. So Luis says, this is one of the coolest things about H5 Coro. We can actually use threading and speed things up. We can also parallelize if even further with Dask. So those are ways that you can speed this up to make it even faster than 5 minutes to run all of this data.
Dask, you could have all those operations, kind of just build a set of things for it to do, and then it will write it out and do all of this. It wouldn't be able to do the like really quite about. And then once you have all this stuff in memory, you could mess around with pixel size or your projection, because you have all the long-term data in there read, so you could do the testing what did you could really do.
Yeah, so Tyler said that once you have it all read in, then you can play with it pretty easily from there without having to do anything substantial otherwise.
Yeah, so please use it and please break it and please talk about it.
The example from the actually using the chunk that they available somewhere.
Yes, if you look on the ICESat-2 GitHub, it's there. But I'll send you the link.
So it's probably in here. What tutorial was it?
It's not a tutorial, it's a project.
Oh, okay.
And I was searching around, I couldn't find a quick way to get this project.
Yeah, it looks like it's not listed here. We'd have to go to the GitHub.
I had it up. So I'll post this down.
Yeah, it'll be in here in their GitHub repo. All right, so we have some remaining time. I want to be cognizant of the fact that people might be flying out. I also have to have a flight. The things that we can do right now is you can ask general questions about, tools and what's coming onto CryoCloud. I could walk you through, basically we went through data access using IcePix and Earth Access. There's also stat catalogs that I have short tutorials for. If you want to access something like I have examples of accessing Landsat data and Sentinel-2 data. We can walk through those really quickly, or we can open up your code and you can try to add some of this data access into your code and run it on CryoCloud. So in that order, anything people are excited about, just type up and we can go through that. Does anyone want to go through data access code?
I would like to do the same stuff, but I think we need to know
Okay.
Can we use the same code and just change the product?
You might, yeah, I mean, I think you could use the read ATL as a template, and then but we have to figure out what data sets you want to read.
Yeah, so when you go to change it, it's basically yeah, where is it? Read ATL. So like these names right here would be different when you, and these right here would all be different in the different data products, but generally this would work once you adjust for those.
And I would say that that's one of the very key things about ICESat is that it has a lot of the, actually I think pretty much it will do for every product, ICESat-2 product, it will generate a list of variables and you have to start picking those variables from that. So that's a very big difference.
So what Andy said is that you can use IcePix to, it'll produce a list of variables for every product. So you can flip through those and choose which ones you want and select only those using IcePix. So that's a nice thing about it.
And if you go to the tutorials in the ICESat, this year's ICESat-2 Hack Week, I have a IcePix tutorial in there that I think explains how to do that. Did you?
Yeah, I'm asking you AG, you're gonna do a session.
Yeah.
And you're gonna have also
Yeah, it'll be on Zoom. I'm still waiting to hear what the logistics of it are. I don't know anything about, I hope they don't charge people. At least I'm gonna, I'll do it on Zoom. Yeah, I'll make sure it's on Zoom. And some of this will be the same. There will be a CryoCloud demo at the beginning so people can learn how to use that. But then we'll get into more of the using Dask, using parallelization. That'll be run by Ellie Abrams. Johnny Kingslake's going to go through AP Res data and how to process that and create cloud optimized data sets and kind of the thought process of how to optimize those data formats. GRIMP is going to be demonstrated by Ian Joggin. Sophie is going to go through GHub and I believe and then yeah, we're going to do some like visualization and whatnot that's kind of similar to the ICESat-2 tutorial we went through, but a different one. And then I'll probably talk a bit about how to open science your publications, so like how to make everything more transparent, reproducible, reusable. Cool. Does anyone want to go? Yeah, go ahead, Ben.
You said you guys went through a lot of different data and how you put those consensus data and just access to NSIDC. I'm interested in your perspective on how to optimize other data sets that I was mentioning radar data that are posted on the CRYSIS server, but usually they're stored as like a MATLAB file. And not that I'm gonna think on this project, but like if you would envision a path or how it would be easiest to move that, what would be your strategy in terms of how to optimize that for cloud?
Some of that, so like there is the option of like actually changing the data format and creating a new copy in a new data format that would make it faster. Tyler or someone can correct me if I'm wrong, but generally you can still like read that data in and stream it depending on the source sometimes, and you won't actually have to download it. You just use the URLs to open it. It's just much slower. Not much slower, but like, I mean, it's much faster than still downloading the data, but that is another option.
Yeah, and with cloud one-dimensional, two-dimensional, the actual format, that's where it might change. It also depends on, do you want written metadata or can you work with a slim file? There's a file type for a long track or just one deep Parquet or Parquet. Those are extraordinarily fast. You can load in data sets that are really seconds. But then when you get into reuse the data set, they kind of saw that I typically use, and if it's just pure 2D, then COGS, the cloud optimized to this. But with Parquet and COGS, you don't have the rich metadata, so it's sort of what you want. You can create, like what Taco said, a stack catalog that can have all that metadata that can drive your COGS. But yeah, okay. But it depends, I guess, on what you want.
Parquet,
Yeah.
There's also a repository put together by the Pangea group, Pangea 4. And what they do, as long as your data, the data that you want to work with is accessible somewhere on the web, then you can basically write a recipe to take that data and to convert it to a cloud optimized format. And they will then review that recipe and figure out, maybe make some changes, or ask you to make some changes, get it working so it's performant. And then they will post that data, run that recipe and post that data in the cloud. So that I don't know. Do you know part of it? I mean, my understanding is it is for free. It's funded by NASA or the NSF, so it's free at the moment.
Do you mind if I email you about that? You said through Pangeo?
Pangeo Forge.
Yeah.
I
don't know great deal. I haven't used it myself, but they are super helpful, super excited to use it.
Yeah.
So that might be worth looking at as well.
For the online people, we just discussed there's a few different kinds of formats, cloud optimized formats that can work for transitioning your code. And then there's Pangeo Forge, or sorry, not code, your data. Then there's also Pangeo Forge, where you can produce a recipe for converting your metadata into something that's more cloud optimized, and that allows that you can host that data in Pangeo Forge for free, and it'll convert it and make it cloud optimized. So yeah, Tyler and Andy are good people to talk to for that. The other thing I want to point you to, we have these tutorials. The ATL10 H5 Coro is in our Jupyter book, and also the ATL15 tutorial we just went through. There's a Landsat tutorial, and a tutorial that kind of goes more through Xarray and Pandas if you want to learn more about those. And then in our how-tos, we have data access and the Sentinel-2 Cloud Access, which is a stack catalog that's included in here to like ways that you can access stack catalog data. So that's any data set that has a stack catalog that often is not in NASA. You can access those. There's other things like how to use the AWS S3 bucket that we have, how to create your own, how to access the Scratch bucket so you can use a lot more temporary storage. The Scratch bucket allows you to quickly read and write data in storage that I think keeps it for 7 days. Yeah, so there's some of that documentation already on our book if you want to access that. I won't walk through it. Anyone who wants to walk through their data or try and read in some cloud data into your current notebooks, we're happy to do that now for a little bit. I think anybody, we can stick around for questions. If anyone has any other questions, we can answer that now. Otherwise, like, you guys can definitely go enjoy the evening, get to your flight, whatever you need to do. Cool. All right. Join Slack. We invite everyone to our Slack, so you can ask us questions there too. Oh, sure. Does anyone online have anything else? Oh.
You sent out an email invite to Slack, or
We just invited you to our Slack. No, I think you were invited a while ago.
yeah.
Thanks everyone for joining online.